So this is the question 1B, where we do the true false rather than the multiple choice. So let's proceed. Metals, alloys, and most ceramics are crystalline materials. Sorry about this R. So what is your answer? Yes, metals and ceramics are crystalline, so this is true. When central atom in the unit cell is surrounded by 8 nearest neighbors, having coordination number 8, crystal structure is called FCC. What is your answer? No. See, when there is a central atom, it is a BCC. On FCC, there are only face atoms. So, right, so definitely this is false, right? So that is the answer. Pure zinc has HCP crystal structure. Now, I don't know if you remember it, but you should. You see, after BCC, FCC, HCP, all of them, the initial introduction, we give a small table of 5, 6, 7 most common metals which belong to that group. So yes, in HCP, zinc is one of the most common metals around. So this is true. Next one, BCC and HCP metals have close packed crystal structure. Remember when you were doing atomic packing factor, you did for BCC, it was say 0.68. You find for FCC, it is higher and so on, right? So here it's a small trick. If this was FCC, then FCC and HCP both are close packed. HCP is of course directly close packed, but we have mixed BCC here, so therefore this is false. BCC is not close packed. If it was FCC and HCP, then it was totally true. Right now it is half true, which means false, right? And here Miller-Bravais indices are used to represent HCP unit cells. So some of you may say that this is outside of the course for now, because in HCP we were not doing the planes and the directions and so on, but as a piece of common knowledge for cubic ones, BCC and FCC, when you are dealing with planes, they are called Miller indices, only Miller indices. But by the time HCP came, another scientist also came, so they are called Miller-Bravais indices when we are talking of planes of HCP unit cells. So this is very true. Okay. Let's move to question 2A of this section. Giving all steps, draw the 1, -1, 0 plane in a cubic unit cell. So first of all, it was just my typewriter in the PC. This is bar 1, right? So when you write it, don't write -1, write bar 1. And giving all the steps does not mean that write any steps. Many people started doing that. It simply means that when your answer is there, it should show all the necessary information, right? So again, pause my lecture video, do it again yourself, and then look at my solution. So if you start the solution now, what are your steps? Of course, it is a cubic cell, so draw the cube. I am repeating myself again and again in the class and here. See, the cube should be very flat. There should be one flat square behind the other flat. Don't be in an oblique angle, don't be in an isometric angle. You are looking from a different view, then it's a very disturbing type of thing. So make sure that your cube, the standard cube, is a standard. Now it is -1 and this is a plane, right? So if it is a -1 in any direction, you change the origin in that axis. This is one step. If it is a plane, you invert all the numbers. Here it will not matter because 1 by 1 is 1, 1 by -1 is still -1. So that is not, so this is it, that draw the cube. In that cube, change the y-axis, make that the starting point, and then start, right? So let us see, right? So you make the cube, and then in y-axis, you move here and mark this point as the origin. So write O here, write 0, 0, 0 in the parentheses here, write new origin. So this is important, that this should be very clearly marked. So now you are done. Now from this origin, in X move 1, right? In X move 1, mark this point, mark this point. In Y, move -1, move -1, mark this point. You are done. So now in your plane, these 2 points are there, therefore join them by a line, this line. Now you have joined this line. Now once you have this line, see that this line is on the base plane, base. So opposite here is the top plane. So draw the same line exactly, draw exactly the same line in the top plane. And once you are done, join them, shade it, this is your plane, right? And don't miss this. This is the final thing, that once the plane is there in the shaded form, any shade you want, then write 1 bar 1 0 here. So now when we say giving all the steps, this is what I mean. That don't just show me this. Show me that this is the new origin, indicate that this is the plane, and the plane is slightly colored or shaded and so on, right? So just like always, this is what you do. Question 2b now. Calculate the planar density for the 110 crystal plane in BCC chromium, which has a lattice constant of this, right? So again, pause my lecture, pause my video, solve it, then proceed. So when you're solving it, always the first thing is to write the knowns. So 110 plane, BCC, chromium is the metal, value of A is this, and the unknown is the planar atomic density, right? So first step, you should know the definition. Planar atomic density means the number of atoms or the number of diameters cut by this plane. The 110 plane is there. So how many atoms are cut by this plane divided by the area of this plane, the two sides. So this is the definition. So how will you start? Again, draw the cube. In the cube, draw the 110 plane. And then see that this 110 plane intersects how many atoms, and then you start, right? So let us see. So that is why I am showing you this, that first we drew the cube and the 110, right? 110, right? One here, one there. So this is the plane. Now this is BCC. So this plane is going right through the central atom, the body-centered central atom. So the central atom is fully there on this plane, and the 4 corner atoms are being cut by it, right? So because it is a plane, so each atom is a circle. These corners are 1 quarter each. So you count 4 into 1 quarter is 1, and this 1. So this is 2 full atoms. Then this is the plane. So this side is A, and this side is the diagonal. So this is A square plus A square and a root. So this side will be root 2A. So the area will be root 2A multiplied by A, and then you are done. So, right, so just see that 1 center atom, 4 corner atoms, total 2 atoms. Area root 2A into A, whatever it is. And therefore the planar density is number of atoms upon the area. Your normal answer should be some number, whatever number comes out to be, per nanometer square. They have here converted it to millimeter square. It is not needed. This is correct, but it is not needed. Let me remind you again that when we are doing normal density, then this is a standard gram per cubic centimeter or kilogram per meter cube. So there we ask you that if it is a standard full density, then convert it to kilogram per meter centimeter square. But here it is planar density. This is only at crystal level. It is not available at any other value. So your answer could very well be number of atoms per nanometer square, and that is it. That is the answer. So now we are moving to question 2a of the other section, right? Of the other section. Giving all steps, show the direction bar 3 to bar 1 in a cubic unit cell, right? So the previous example was a plane. This time it is a direction indices. So once again, pause it here, solve it, and then come back to the solution. So in a direction unit, you know that again, if there are any minus signs on any axes, you shift the origin. This is one thing. And if any of the numbers are larger than 1, then make sure that you divide by a number so that everything is 1 or less. So in this case, you will have to divide by 3 so that the largest number becomes 1 and the others become smaller than that. And then you start again, make a very nice cube. In that cube, shift the origin and then just count the things and draw the arrows, right? So let's see. So this is here. I have missed one step writing here, that you write here that we divide by 3. So now your values are bar 1 by bar 1, 2 by 3, and bar 1 by 3. This is important. Then you draw the cube. You draw the cube, right? X-axis move. Y-axis don't move. Z-axis move. So this is your final origin. Remember, right? Minus here, minus here. So move in X-axis, move in Z-axis. Mark this as O, the new origin. Once it is there, then -1 in the X-axis, -1. So you go from here to here. So you are there, -1. Then plus 2 by 3. So 2 by 3 in the Y. And then -1 by 3. So -1 by 3 here. And this is your final point. Mark this. Join origin to this one. This is your arrow. Make it darker so that it is shown as an arrow, right? So when I say show full steps, it means you show that one line where you are converting this to 1, 2 by 3, -1 by 3. And then have this thing, show that this is the new origin, show these distances, 2 by 3, 1 by 3. And finally, once the arrow is there, once the direction index is there, write this, that 3 bar 3, 2 bar 1 in brackets. So then you are doing all the given steps. Okay, so this is the solution. So now it is question 2B of the next section, second section. The question is, values of atomic mass, density, and atomic radius for a metal alloy are this, this, and this. Determine whether its crystal structure is FCC or BCC, right? So once again, just note down what is given and not given. Mass, this value. Density, this value. Atomic radius, this value. Remember, mass is in gram per mole. So this is known. And they are asking whether this is FCC or BCC. So in the solution, you first assume that, okay, I assume that it is FCC. If it is FCC, then you write that FCC will have 4 equivalent atoms. And for FCC, the equation is A is equal to 4R upon root 2. Density, right? The equation of density is mass per unit volume. So mass per unit volume at the crystal level means mass of the number of atoms in that unit cell divided by the volume of the unit cell, which is always A cubed. So this is it. So find this for FCC, right? Find the density like this. Number of equivalent atoms multiplied by the mass of one atom, divided of course by Avogadro's number, because when the mass is in gram per mole, you do that. So do that for FCC, you get some density. Do that for BCC, the same thing, that BCC, there are 2 equivalent atoms. The equation is A is equal to 4R upon root 3. Substitute this in the density equation, find the density. Whichever one of them matches the given density, then that is your answer, right? So this is it. So let us see, right? We are doing exactly the same thing. FCC, A is equal to 4R upon root 2. There are 4 atoms. You plug in all the values, you find the density. BCC, 2 atoms, A is equal to 4R upon root 3. You find the density. This is the answer. This answer is 6.97 gram per cubic centimeter. This is almost 6.4 gram per centimeter cube, which is the given density. So therefore the answer is BCC. If by chance you had selected BCC first, then you don't need to do FCC. You do just BCC and say that the density is exactly what is given. So the structure is BCC.